Let us work few problems related with the shift registers. A 4-bit right shift register, initial content is 0101. After 2 clock pulses, what is the content of the register? It is the question. So the initial content we are looking at 0101. After 2 clock pulses, the question is after 2 clock pulses, what is the content the register? What is the content of the register after 2 clock pulses? We need to work like this. Nothing is mentioned so that you can consider default. It is a flip-flop corresponding to the MSB and so on. It is a flip-flop corresponding to LSB. Hence Q3, Q2, Q1, Q0 are the respective flip-flop outputs. Q3 is the MSB flip-flop output, Q0 is the LSB flip-flop output. So we are looking here. Initial content in the register is 0101 and serial input. We are reading by using exclusive OR gate, so that it is a exclusive OR between Q1 and Q0. Before applying any clock signal, what is the serial input? If you look, the serial input 0 exclusive OR 1 is 1. So that as and when we are applying the clock signal, the content in the register is 1, 0, 1, 0. So that these bits are shifting to the right and the serial input data is coming to the MSB flip-flop. Now before second clock pulse, what is the serial input? If you look, Q1 exclusive OR with Q0, 1 exclusive OR with 0 is 1. So that after second clock pulse, we'll be having the content in the register as 1101. Hence, answer to this question 1101. It is the content of the register after 2 clock pulses. It was a question couple of times in the GATE exam in the IES papers. Of course, not a very difficult question, very straightforward, simple question only. Let us try for one more question. Here we are looking at a question. A 4-bit right shift. It is a right shift. Okay. A 4-bit right shift register is shifting the data to the right for every clock pulse. The serial input D is derived by using exclusive OR gates as shown in the figure. So it is a 4-bit shift register, serial input D, which is derived by using these exclusive OR gates, so that you can able to read the D input is nothing but exclusive OR between Q3, Q2 and Q0. So 1 bit we are looking, the initial content in the register is 1000 at Q0, Q1, Q2, Q3. After how many clock pulses this circuit, that is the register, is back to initial state? It is 1 bit. Second bit, after a clock pulse, the content in the register is to be 1010 at Q0, Q1, Q2, Q3. What will be the initial content of the register? It is a second bit. It was a question in the GATE exam 1996. It is a good question. Try to keep attention and try to identify. In the description of the question, there is a small hidden thing. We need to identify that hidden thing well. That is very important to conclude the answer properly. It is a right shift register. Once it is a right shift register, the data will be shifting from MSB to LSB. Based on this problem description, based on this figure, MSB bit is flip-flop 3 output, that is Q3. LSB bit is flip-flop 0 output, that is Q0. So the data will be shifting from flip-flop 3 to flip-flop 0. So while looking to this figure, normally the mistake what we will be doing is, while looking Q0 nearer to the D, what is the serial input D is entering, mostly we will be trying to transfer the serial input D first to flip-flop 0. It is wrong. The serial input D is not transferred to the flip-flop 0 first. The serial input D will be transferred to the flip-flop 3 first. That is the hidden thing. instead of the notation Q0, Q1, Q2, Q3, if at all we are looking the notation as something like this: QA, QB, QC, QD. Then if I am in the problem description, if at all we are not talking which is LSB, which is MSB, default you can consider QA is MSB and so on, QD is LSB. But whenever we are having a description with a decimal subscripts like this, it is not allowed to consider Q0 is MSB. Highest decimal number is MSB. It is a block diagram representation. In this question paper in the 96, it is given intentionally to make the student for proper attention purpose. Instead of this notation, even if at all I am looking something notation like this: Q2, Q1, Q3, Q0, even if at all we are talking like this, default the means the only block diagram representation, Q3 is MSB and so on, Q0 is LSB. While looking to the Q2 nearer to the D, it is not the means the Q2 is MSB. So this thing, if at all we are taking care properly, the question is not difficult. Most of the students will be doing the mistake while considering simply Q0, that the D is transferred to the Q flip-flop 0, while taking the Q0 as MSB, people will do the mistake. It is very clearly mentioned in the right shift register. Once is the right shift register, the data will move always from MSB to LSB. With the left shift register, the data will shift from LSB to MSB. It is standard notation, unless it is not mentioned specifically. So while taking care like this, if you look to the solution of the A bit, for our working purpose, it is better to keep the notation from Q3 to Q0. Serial input D, initial content 1 0 0 0 at Q0, Q1, Q2, Q3. Now, based on the question, we need to go on apply the clock pulses until the register is back to the initial state. So after how many clock pulses it is back to the initial state, that is the answer we need to give for A bit. Before the first clock pulse, if we look to the serial input, it is the exclusive OR between Q3, Q2, Q0. So be clear, as far as the serial input D is concerned, Q1 is not coming into the picture. So mostly we may do the mistake in a hurry while looking to the serial input D, also taking the Q1 into account, we may do the mistake. There is also other mistake, it is possible. Anyway, if you look here, 0 0 1, hence odd number of variables are 1, serial input D is 1. Now if you apply the clock signal, we are looking, it is the content we are having, we are looking in the register. Before second clock pulse, we look to the serial input Q3, Q2, Q0, 1 0 0. So again it is 1. The second clock pulse, we are looking, it is the content. And before third clock pulse, Q3, Q2, Q0, even number of variables are 1, so that exclusive operation result becomes 0. If you apply third clock pulse, we are looking, it is the content in the register. As we know, as per the question, we are supposed to go on apply the clock pulses until we are back to initial state. It is not back to the initial state, we are going further. Before fourth clock pulse, Q3, Q2, Q0, if you look, it is 1. In the fourth clock pulse, we are looking, it is the content. Before fifth clock pulse, if you look, Q3, Q2, Q0, 0. The fifth clock pulse, we are looking, it is the content. It is not the initial state, so we are going on applying. Before sixth clock pulse, Q3, Q2, Q0, 0. So that we are looking, it is. Before seventh clock pulse, if you look, Q3, Q2, Q0. Q3, Q2, Q0, it is 0. So that after seventh clock pulse, we are looking, the circuit is back to initial state. Hence, answer to this A bit, the answer to the A bit, we are looking as 7. The circuit is back to initial state after seventh clock pulse. It is the correct answer. But wrongly, if you take D is transferred to the Q0 first, then the answer you are not going to look as 7, you will be looking to the wrong answer is 6. A small thing will be having that make you to give the wrong answer. Okay, coming to the B bit. Based on the question description, after a clock signal, the content in the register is to be 1010. After a clock signal, we want to read the content in the register is to be 1010 at Q0, Q1, Q2, Q3. What will be the initial content of the register is the question. So if you look here, after a clock signal, if you want to read Q3 to be 0, then D must be, serial input must be 0. After clock signal, we want to read the Q2 to be 1, then Q3 must be 1, Q1 to be 0, so that Q2 must be 0, Q0 to be 1, so that Q1 must be 1. So we are looking here, Q3 is 1, Q2 is 0, and we want to read D is to be 0, then what will be the Q0 is the question. So if at all we are talking Q0 as 1, then only the serial input D becomes 0. Hence, Q0 must be 1. Hence, the answer, if you look, the answer by mistake people may write as 1011. It's the wrong answer. The answer will be 1101. No doubt, if it is a multiple choice question, A bit may be, option A may be this, option A may be this, it may be some C or D. It is the wrong option. The correct answer will be this. The reason is, everywhere in the problem description, the order is mentioned from Q0 to Q3. Default, the answers what we are looking in the multiple choice, they are also with the same order Q0 to Q3. Hence, the answer will be 1101. So, it is the answer. It is one of the good question, and we will be having generally the questions of descriptive as well as objective of this nature from this shift register topic. Take previous question papers and look to the problems of shift registers. Mostly you will be having a problems of this type, and you will be having some questions related with the shift register application. Sometimes you will be having questions in the match the following. In the list A, you will be having shift register, decoder, something items like this, some devices like this, and in the list 2, you will be looking generally the applications of each one of the devices which is present in the list 1. So in the list 2, generally you will be looking one of the application of the register. So these are the generally scope of the questions in this topic. When we are using n-bit shift register as a counter, we are having a possibility to count maximum 2n number of clock pulses. Of course, we are using the shift register as Johnson counter or Mobius counter. When we are using the register as a Johnson counter or Mobius counter, the maximum count is possible to a number of clock pulses. The example what we considered of 4-bit register. So by using 4-bit register, when we are using register as a counter for when we are looking to the maximum count, now we are not using as a ring counter. We need to look as a twisted ring counter or as a Johnson ring counter or Johnson counter. So when we are using a Johnson counter, we are able to count maximum 8 clock pulses. But we know that with a group of n flip-flops, we are having possibility of to the power of n number of combinations. Out of to the power of n number of combinations on the group of n flip-flops, when we are using the register as a counter, we are able to use only 2n number of clock pulses. We are able to count only 2n number of clock pulses. Means we are able to use only 2n number of states out of to the power of n number of states are possible. So that we are unable to use all possible states for the counting of the clock pulses when we are using the register as a counter. Of course, register is basically developed as a storage device. As extra application from the storage device, from the register, we are having this counter operation. There are specially designed circuits. In these specially designed circuits, the group of n flip-flops, we are having possibility to count to the power of n number of clock pulses. These specially designed circuits which are used for the counting of the clock pulses, such circuits we are naming as counters. So that if you want to count 8 clock pulses, then no need to use 4 flip-flops. For counting of the 8 clock pulses, only 3 flip-flops are enough. With a group of 3 flip-flops, we are having total 8 states, so that when we are using, when we want to have the mod 8 counter, instead of using 4 flip-flops, when the case of the register, we can use only 3 flip-flops. So anyway, there are specially designed circuits for the counting of the clock pulses by using minimum number of flip-flops. Such circuits we are naming as counters. If at all we are looking the broad classification on the sequential circuits. The broad classification of the sequential circuits most of the times is with respect to the clock signal. Based on the clock signal, we are having the sequential circuits as asynchronous sequential circuits and synchronous sequential circuits. In the case of asynchronous sequential circuits, external clock is not common to all the flip-flops. Whereas in the case of the synchronous sequential circuits, external clock is common to all the flip-flops. As and when external clock is common to all the flip-flops are getting chance to change their values simultaneously. But as and when external clock is not common to all the flip-flops, then all the flip-flops may not be getting chance to change simultaneously. So it is a difference between the asynchronous sequential circuits and synchronous sequential circuits. So the difference is based on the clock signal. So this is the classification we are looking at higher level on the sequential circuits. We are looking many examples for the sequential circuits such as sequence detectors, parity generators, counters, etc. Many other circuits we are having as a sequential circuits. So in all these circuits we are having a possibility of this asynchronous operation and synchronous operation. So with consent to counters, if at all we are looking, we are having the possibility of asynchronous counters and synchronous counters. So in the case of the asynchronous counters, clock is not common to all the flip-flops, whereas in the case of the synchronous counters, clock is common to all the flip-flops. Having common clock to all the flip-flops, synchronous counters definitely will be faster than asynchronous counters, because having a common clock pulse, all the flip-flops in the counter are changing simultaneously. While not having a common clock pulse, all the flip-flops may not be changing simultaneously. Hence, synchronous counters are faster than asynchronous counters. Let's work first for asynchronous counters. For realizing standard For realizing standard asynchronous counter, we are having possibility to use JK flip-flops, T flip-flops we can use directly, but we are not having a possibility to use SR flip-flops, D flip-flops to use directly. I am talking with a prefix word of directly. We are unable to use the SR flip-flops and D flip-flops directly to realize standard asynchronous counter. Again, I am not talking simply asynchronous counter. I am using again a prefix word before this asynchronous counter as a standard. There is a meaning of the standard. We will be looking to the meaning of the standard asynchronous counter also. But anyway, we will be looking back to this statement after developing a circuit. A standard asynchronous counter can be developed directly by using JK flip-flops or T flip-flops, but not with SR flip-flops or D flip-flops. Let us try here a standard asynchronous counter by using JK flip-flops. Let us take a case of 3-bit standard asynchronous counter. So once we are talking it is a 3-bit, we need to use 3 flip-flops. So in this 3-bit asynchronous counter, we are using JK flip-flops. It is the MSB flip-flop and so on. This is the LSB flip-flop for this 3-bit case. So that we are naming LSB flip-flop as a flip-flop 0. Here it is a flip-flop 1, it is a flip-flop 2. All the flip-flop clear terminals are connected to the common terminal. All the flip-flop preset terminals are connected to the common terminal. All the flip-flop J and K inputs are connected to the logic 1. And we are looking. Flip-flop 2 clock is coming from the flip-flop 1 output. Flip-flop 1 clock is coming from the flip-flop 0 output. External clock is coming to the flip-flop 0 directly. So based on this, in general, if at all you are looking, LSB flip-flop clock is coming from the external source. For the remaining flip-flops other than LSB, flip-flop I clock is coming from the flip-flop I minus 1 output. Output of the flip-flop I minus 1, that is in complementary output in this circuit, is the clock of flip-flop I. It is a connection what we are looking. And we are looking all the flip-flop J and K are connected to the logic 1. Whenever J and K are connected to the logic 1, basically the flip-flop becomes a toggle flip-flop. You can say it's a T flip-flop with T is connected to 1. Whenever T is connected to 1, we know well for effective clock signal the flip-flop output is going to be complement. For any effective clock signal, the flip-flop is going to be complement from the previous value. Any asynchronous counter, as and when it is having this sort of connection, such circuit only we are naming as standard asynchronous counter. It is the meaning of standard asynchronous counter. As and when we are having a asynchronous counter with this sort of connection, that is a clock of the flip-flop I coming from the flip-flop I minus 1 output, and LSB clock is from the external source, and the JK inputs are T inputs of the flip-flops. If you replace this JK with the T, it becomes the T input. So JK inputs are connected to 1. Such asynchronous counter only we are naming as a standard asynchronous counter. Instead of this, suppose we are having a counter circuit something like this. If at all we are having a counter circuit something like this we are not naming as standard asynchronous counter. It may be asynchronous counter, but it is not a standard asynchronous counter. In the standard asynchronous counter, expected connections for the clock supposed to be like this. Then only that asynchronous counter we are naming as standard asynchronous counter. Now, before going to apply the clock signal to the circuit, we want to read all the flip-flop outputs to be 0. We want to read this Q3, Q2, Q1, Q0. All these flip-flop outputs we want to read as 0. So to read all the flip-flop outputs to be 0, clear must be connected to 0, preset must be connected to 1. After connecting clear 0 preset 1, all the flip-flops we are going to read with output as 0. Later we want to apply the clock signal. To apply the clock signal, the clear and preset must be ineffective, so that they must be connected to 1. Clear and preset must be connected to 1. So it is a required initial setup before going to apply the clock signal. Later we are going to apply the clock signal. Now, based on the connections, it is possible to recognize easily Q0, that is the flip-flop 0 output, will change for every clock pulse, because external clock is coming to the flip-flop 0 directly. As and when there is a clock signal, the flip-flop 0 is getting a chance to change. It is going to be complement from the previous state. Coming to flip-flop 1, that is a Q1, flip-flop 1 output Q1 is getting chance to change its value if and only the Q0 is changing from 1 to 0. The reason why, if at all you are taking the question, because of the answer to this question is because of the negative stick guide. Because the negative stick guide, effective clock is coming to flip-flop 1 as and when the Q0 is changing 1 to 0. In other way, if at all the Q0 changing 0 to 1 or 1 to 1 or 0 to 0, these changes of the Q0 is not giving clock effect on the flip-flop 1. Similarly, if you look at the flip-flop 2 output, that is Q2, Q2 is getting chance to change its value if and only Q1 is changing from 1 to 0. In other way, whenever Q1 is changing either 0 to 1 or 1 to 1 or 0 to 0, that is not giving clock effect on the flip-flop 2. So knowing this, it becomes easy for us to work while applying the clock signal to read the operation of the circuit. So while applying the first clock pulse bit, so that Q2, Q1, Q0. So while applying the clock signal, Q0 has to change for every clock signal. It is changing 0 to 1. Whenever Q0 changing 0 to 1, that is not the clock to the flip-flop 1, so that no change to the flip-flop 1, so that there is no change to the flip-flop 2. If at all the Q1 is not changing, we should not talk anything about the flip-flop 2 change. It's not possible. So no need to think, no need to waste time to think on the flip-flop 2 whenever the Q1 is not changing. It is a content in the counter after first clock pulse. With the second clock pulse, for every clock pulse Q0 has to change, it is changing 1 to 0. Whenever Q0 is changing 1 to 0, it is a clock to the flip-flop 1, so that the flip-flop 1 has to change. It is changing 0 to 1. Whenever the Q1 is changing 0 to 1, that is not the clock to the flip-flop 2, so the flip-flop 2 is not changing. The third clock pulse, Q0 changing 0 to 1. Whenever Q0 changing 0 to 1, it is not the clock to the flip-flop 1, no change in the flip-flop 1. Once the flip-flop 1 is not changing, no chance to the flip-flop 2 to change. So flip-flop 2 will remain 0. With the fourth clock pulse, Q0 changing 1 to 0, it is the clock to the flip-flop 1. Flip-flop 1 has to change. It is changing 1 to 0. Whenever the Q1 is changing 1 to 0, it is the clock to the flip-flop 2. It has to change. And so on like this, we supposed to go on apply the clock pulses until the circuit is back to initial state. After 7th clock pulse, all the flip-flops are the value of 1. The 8th clock pulse, Q1 is changing 1 to 0. It is a clock to the flip-flop 1. It is changing 1 to 0. The clock to the flip-flop 2, so it is changing 1 to 0. Circuit is back to initial state after 8 clock pulses. Hence, we need to name this circuit as mod 8 asynchronous counter or divided by 8 asynchronous counter. A standard asynchronous counter also named as ripple counter. Not any asynchronous counter, only a standard asynchronous counter can be named as a ripple counter. The word ripple is having a meaning of the propagation, and if you look here, the propagation is for what? But all what we are talking for worst case. Worst case is the case in the case of the counter when all the flip-flops are changing, it is the worst case. Suppose consider presently we are looking to the content in the counter is 110. We are having 110 presently. We can able to look here from outside. Whenever we are applying the clock signal, first flip-flop 0 changing 120. It is the clock to the flip-flop 1. So the flip-flop 1 is changing 120. It is the clock to the flip-flop 2. So the flip-flop 2 is changing 0 to 1. So from the user, if at all we are looking, from the user view, if at all you are looking, you are looking from outside. The clock what we are applying at LSB, which is looking to be passing through every flip-flop from LSB to MSB. It is a reason to name a standard asynchronous counter as ripple counter. Here, of course, in our discussion, we are looking to only the standard asynchronous counters or ripple counters. We may be looking to one or two examples later. Not a ripple counter, we'll look later. But at this moment, we are discussing only the standard asynchronous counters or ripple counters. So, based on this, you can name it is 3-bit or mod 8 or mod divided by 8 ripple counter or asynchronous counter. And we said we can use JK flip-flops and T flip-flops directly. Why it is so, we can understand easily. They may be JK flip-flops, but based on the connections, all the flip-flop J and K inputs are connected to 1. So it is effectively we are using as a toggle flip-flop. And we said we are unable to use SR flip-flops and D flip-flops, of course, with the prefix word, use a word as a directly. You can understand why it is so. SR flip-flop, in the SR flip-flop 1-1 is not allowed, so not possible to use directly. D flip-flop also the same problem. What is the flip-flop we want to use in the standard asynchronous counter, ripple counter, those flip-flops we are expecting direct operation with the T. For SR and D, direct operation with the T is not possible. But of course, we are not talking not possible to use. If you convert the SR flip-flop to T, or if you convert the D flip-flop to T, then it is allowed to use. So any flip-flop can be converted to any other flip-flop, that is there always, but with extra additional hardware we need. We are unable to use directly, but if you convert to T flip-flops, this SR flip-flop or D flip-flop, then we are allowed to use. This table content we can convert as a figure. That means this table content we can look as a timing diagram. Let us try for that. So let us take a sample work with the 10 clock pulses. Let us draw first the flip-flop 0 output, that is a Q0 LSB flip-flop output. Initially it is 0. The first clock pulse it is 1. So having the negative trigger, the changes will be looking whenever the clock is changing 1 to 0. So after first clock pulse it is 1. After second clock pulse it is 0. In fact, no need to look even this table. From this clock itself we can able to draw the waveform for the Q0. Whenever the Q0 changing 1 to 0, there will be change. Whenever clock is changing 1 to 0, there is a change in the flip-flop 0 output. So looking to this clock itself, we are having possibility to draw this waveforms. And looking to the Q1, Q1 is getting chance to change its value whenever Q0 changing 1 to 0. So based on this, you can see initially it is 0 until to the second clock pulse. After second clock pulse it is 1. Again Q0 changing 1 to 0 at the fourth clock pulse. So at the fourth clock pulse it is 0 and so on. We can look like this. And Q2 if you look, initially it is 0 until to fourth clock pulse. After fourth clock pulse it is 1. Or equivalently directly you can see whenever Q1 is changing 1 to 0, it has to change. It is changing 1 to 0, it has to change, and so on. So it is the timing diagram what we are having for this 3-bit ripple counter. If at all we are looking the repetition time at the flip-flop 2 output, consider the clock repetition time is TC. The repetition time if at all we are looking at the flip-flop 2 output. the repetition time at the flip-flop 2 output will be 8 into Tc. So based on this frequency of the flip-flop 2, if at all we are looking, it is coming to be 1 upon 8 into Tc. So it is a clock frequency by 8. Hence, if at all the clock frequency is 1 kilohertz, from the flip-flop 2 output we will be looking to the frequency as 125 hertz or 125 cycles per second. In fact, it is a reason to name this counter as divided by 8 counter. The meaning of the divided by 8 is the division of the clock frequency with the decimal number 8. As a matter of interest, if at all we are looking at the frequency of the flip-flop 1 output. The flip-flop 1 output, if we look to the repetition time we are looking as 4 into Tc, so that the frequency of the flip-flop 1 output will be clock frequency by 4. Similarly, if at all we are looking the frequency calculation at the flip-flop 0 output, the repetition time is 2 Tc, so that it is a clock frequency by 2. When we are using this as a divided by 8 counter, internally from the flip-flop 1 we are looking to the divided by 4 operation, from the flip-flop 0 we are looking to the divided by 2 operation. In fact, if we want only divided by 4 operation, then definitely we are not in need to use 3 flip-flops, 2 flip-flops are enough. If we want to have the divided by 2 operation, then of course only 1 flip-flop is enough. This circuit, let us name circuit 1. In this circuit 1, let us try to do small modification. The modification what we want to do in this circuit 1 is, the clock of the flip-flop 1 is from the flip-flop 0 Q0 complement. The clock of the flip-flop 2 is from the flip-flop 1 Q0 complement. This is a modification we want to do, so that external clock is similar to circuit 1, here also coming directly to the flip-flop 0. This modified circuit let us name as circuit 2. Now, for this modified circuit, while applying the clock signal, we want to verify the operation. In fact, basically we want to try to identify the mod value, and also we will try to identify the switching sequence. Here also, before applying the clock signal, we want to read all the flip-flop outputs as 0, 0, 0. To read all the flip-flop outputs to be 0, 0, 0, as usual, clear must be 0, preset must be 1. Later, we want to apply the clock signal. To apply the clock signal, the clear and preset both must be connected to 1. Based on these connections, here also we can look JK inputs are connected to 1, so that as and when there is effective clock signal, the flip-flops are going to change. And you can see further in detail based on the connections. Flip-flop 0 here also getting chance to change its value for every clock pulse, because external clock is coming directly to the flip-flop 0. Coming to flip-flop 1 is getting chance to change its value if and only the Q0 complement is changing 1 to 0, because it is the clock to the flip-flop 1. Whenever Q0 complement is changing 1 to 0, then only it is an effective clock, it is a negative edge triggered. In other way, whenever Q0 is changing 0 to 1, then the flip-flop 1 is getting chance to change. And coming to the flip-flop 2, it is getting chance to change its value if and only the Q1 bar is changing from 1 to 0, or equivalently speaking, whenever Q1 is changing 0 to 1, at that time the flip-flop 2 will be changing. So with this understanding, it is very easy for us to go further work while applying the clock signal. So while applying the first clock signal, Q0 is changing 0 to 1. Whenever Q0 changing 0 to 1, it is a clock to the flip-flop 1. so the flip-flop 1 will change. When Q1 is changing 0 to 1, when Q1 is changing 0 to 1, it is a clock to the flip-flop 2, so flip-flop 2 has to change. It is a content we are looking in the counter after first clock pulse. The second clock pulse, Q0 will be changing 1 to 0. Whenever Q0 changing 1 to 0, whenever Q0 changing 1 to 0, that is not the clock to the flip-flop 1, no change to the flip-flop 1. Once no change to the flip-flop 1, no change to the flip-flop 2. The third clock pulse, Q0 changing 0 to 1, the clock to the flip-flop 1 is changing 1 to 0. It is not the clock to the flip-flop 2, no change. And so on. We can look like this. We supposed to go on apply the clock pulses until the circuit is back to initial state. After 7th clock pulse, the content in the counter is 001. The 8th clock pulse, the circuit is back to initial state. Hence, this also we supposed to name as mod 8 or divided by 8 asynchronous counter or ripple counter. Both these circuits, circuit 1 and circuit 2, both are mod 8 or divided by 8 asynchronous or ripple mod 8 counters. But based on the switching sequence, there is a difference between the circuit 1 switching sequence and circuit 2 switching sequence. The circuit 1 switching sequence, we are looking to the sequence in the decimal form if at all. If you look 0, 1, 2 and so on 7 back to 0. Whereas in the circuit 2, the switching sequence if you look, it is 0, 7, 6 and so on 1 back to 0. Based on this switching sequence difference, we are having a possibility to give the distinguishable names for circuit 1 and circuit 2. Circuit 1 we are naming as mod 8 or divided by 8 or simply a 3-bit ripple or asynchronous up counter. Whereas circuit 2 we are naming mod 8 or divided by 8 or 3-bit ripple or asynchronous down counter. Whether it is a up counter or down counter with this negative edge triggered, basically we need to remember like this. For up counter purpose, for negative edge triggered, we are looking uncomplementary flip-flop outputs are the inputs to the next flip-flop. LSB clock is from the external source. For down counter, complementary outputs of flip-flops are the input of the clock and external clock is coming to the LSB directly. So it is a thing what we need to remember. Let's look few small changes in the circuit 1 as well as circuit 2. Suppose in the circuit 2, the one which is available on the board, consider the flip-flops instead of negative edge triggered. Assume the flip-flops are the positive edge triggered clock. Consider the flip-flops are positive edge triggered clock. It is the modification what we are looking in the circuit 2. With this modification, if we want to look what is the mod value and what is the switching sequence of the counter, it is possible to understand external clock is coming directly to the flip-flop 0, so that flip-flop 0 will change as similar to the earlier circuits for every clock signal. Flip-flop 1 is concerned, it is getting a chance to change its value if and only Q0 complement is changing 0 to 1, because here it is a positive edge triggered. Once we are talking the Q0 bar is changing 0 to 1, then the flip-flop 1 is changing. Equivalently, we are having a possibility to speak. Whenever Q0 changing 1 to 0, then flip-flop 1 will change. Coming to flip-flop 2. Flip-flop 2 is having a chance to change its value whenever Q1 complement is changing 0 to 1. Or equivalently, it is possible to speak as whenever Q1 is changing 1 to 0, at that time the flip-flop 2 will change. So with this understanding, without going to further details, it is possible to speak for us. With this understanding, we are able to speak now at this moment the circuit 2 switching is supposed to be very similar to the circuit 1 switching. Because in the circuit 1 switching, we were able to see flip-flop 0, no need to discuss. For every clock pulse, it will change. Flip-flop 1 was changing the circuit 1 whenever the Q0 was changing 1 to 0. Flip-flop 2 was changing whenever the Q1 was changing 1 to 0. So it is very similar to circuit 2 operation, very similar to circuit 1. Hence, it is possible to speak now it is up counter. So that in this circuit 2, you can speak now in this circuit 2, while replacing negative edge triggered flip-flops with positive edge triggered flip-flops, while replacing negative edge triggered flip-flops in the circuit with the positive edge triggered flip-flops, the circuit becomes up counter. So it is a 3-bit. So the 3-bit up counter or mod 8 or divided by 8 ripple or up counter. As similar to this, it is possible to speak now circuit 1 when we are replacing this negative edge triggered flip-flops with the positive edge triggered flip-flops, it becomes a down counter. It becomes a down counter. Here we consider the examples of 3-bit. If you want 4-bit, 5-bit or in general of any size, it is story what we are looking with respect to this ripple up counters or down counters. Let's look a circuit of 3-bit up down asynchronous counter or ripple counter. Let's name it as circuit 3 because we named earlier 2 circuits as circuit 1 and circuit 2. Here external clock is coming to the flip-flop 0 directly, which is similar to the for circuit 1 and circuit 2. The clock to the flip-flop 1 by using this 2-level AND OR circuit. The clock to the flip-flop 2 by using another 2-level AND OR circuit. And all these flip-flops, just for our comfort, we consider as a T flip-flops. T inputs are connected to 1. Here in this circuit, we are not looking to the preset and clear terminals. The default we need to understand the preset and clear terminals after clearing all the flip-flops are connected to the logic 1. Just for our convenient, we are not putting, but other way the meaning is same. After clearing all the flip-flops, they are connected to the logic 1. Let us name it is A1, this as a B1, this as A2, this as B2. There is external input M is coming to the flip-flop A1 and A2 directly, whereas for B1 and B2, M is coming after this NOT gate. So based on this, it is possible to understand operation easily. Whenever M is 1, the status of AND gate A1, A2 and the status of AND gate B1 and B2, if you look, A1, A2 gates are enabled, B1, B2 gates are disabled, because M complement is the input to the B1, B2. Whenever M is 1, M complement is 0. One of the input to the B1, B2 is 0, so that the B1, B2 gates are disabled. And one of the input of A1, A2 are 1, so that A1, A2 gates are enabled. Now based on this, it is possible to look whatever the output we are having from this 2-level AND OR, it is because of the second input of the gate A1. Similarly, what is the output we are having from this 2-level AND OR, it is second input of A2. We know well, based on the connections, second input of A1 is Q0, so that Q0 is coming as directly clock of the flip-flop 1. Second input of A2 is Q1, Q1 is coming directly as a clock of the flip-flop 2. And now you can check the circuit 3 at this moment with M is 1 is equal to the circuit 1. Hence, it becomes up counter. No need of any further discussion required. It becomes now up counter. Similarly, whenever M is 0, whenever M is 0, it's the reverse. The gate A1, A2 are disabled, gate B1, B2 are enabled. So at this moment, if at all we are looking to the status of the 2-level AND OR circuits, the 2-level AND OR circuit output is now depending upon the gate B1 and B2 outputs. The gate B1 output is depending upon the second input of the B1. Second input of B1 is Q0 complement. So that Q0 complement is now coming as a clock of the flip-flop 1. Similarly, the second input of the B2 is the output of this two-level AND/OR circuit. The second input of the B2 is Q1 complement. So that Q1 complement is a clock of the flip-flop 2. We know well at this point of time, the circuit 3 we can able to speak it is equal to circuit 2. So we know well circuit 2 was down counter. So that with ME 0 the circuit operation becomes down counter. The circuit is having based on M value up sequence as well as down sequence. Based on this we are naming it is a 3-bit up down ripple counter or up down asynchronous counter. We considered here for 3-bit case, we want 4-bit or 5-bit, it is going to be the similar extension work we need. And also of course you can see these two-level AND/OR blocks we can replace even with the multiplexers of size 2 by 1. It is also possible. So anyway, it is a up down asynchronous counter. Let us take a question. It is a given counter, ripple counter circuit. The question is 1 bit. What is the mod value of the given ripple counter? The next bit on the same circuit, draw the waveform of the NAND gate output P. Draw the waveform of P. It means the P is nothing but the NAND gate output. We want to draw the NAND gate output P waveform. It is a question. So to draw the waveform of the NAND gate output P, first of all, we need to recognize the mod value. For that, we need to know the switching sequence. From that, it is possible to draw the waveform. Analyzing the circuit in a simplest way if we want to look. Suppose there is no any such NAND gate. If at all there is no any such NAND gate in the circuit and the clear is connected to 1, then we know well it is similar to the circuit 1. If there is no NAND gate in the circuit and a talking clear input is connected to 1, then it is same as circuit 1. We know that circuit 1 switching sequence initially it is 0 0 0. While applying the clock signal we are looking to the switching sequence something like this. So circuit 1 was mod 8 ripple counter. It was the switching sequence of the circuit 1. Now in this question the problem is the NAND gate output is coming as the clear input of all these flip-flops. NAND gate output is coming as a clear input of all these flip-flops. Even for this, based on the circuit 1 operation, it is possible to understand as long as this NAND gate output is 1. As long as this NAND gate output is 1, then the clear is connected to 1. Even now also we can see the circuit operation supposed to be similar to the circuit 1 switching sequence. It must follow this switching sequence. But as and when the NAND gate output is changing from 1 to 0, then the clear input is coming to be 0. Definitely at this moment the circuit operation is not similar to the circuit 1 switching sequence. Whenever the clear input is coming to be 0, there will be disturbance in this normal switching sequence. There will be deviation in this normal switching sequence. Exactly what is happening we'll discuss later, but we are guaranteed there is a disturbance in this normal switching sequence. But we are very much sure as long as this NAND gate output is 1, this circuit will follow the switching sequence of the circuit 1. Now if we look further, as long as one of the input of this NAND gate is 0, then guarantee this NAND gate output is 1. As long as one of the input of this NAND gate is 0, we are guarantee the NAND gate output is 1. You can see from this available table, the NAND gate inputs are coming from the flip-flop 2 and flip-flop 1 outputs. Among the flip-flop 2 and flip-flop 1 outputs, if at all we are looking, before 6th o'clock pulse, if you see, before 6th o'clock pulse, if at all we are looking, we are guarantee among this Q2, Q1, one of the flip-flop output is guarantee as 0. so that without any further understanding, it is possible to speak the p value before 6th clock pulse without talking anything. We are able to speak it is 1. As long as one of the input of the NAND gate is 0, the NAND gate output is 1. Whenever you are trying to look to the waveform for this B bit, then no need to go more number of clock pulses. Few clock pulses are enough to draw the waveform. Suppose it is the 5th clock pulse, it is the 6th clock pulse, and we are looking to the waveform to the NAND gate output P. It is 1 even after 5th clock pulse. Even after 5th clock pulse, this NAND gate output is 1. This NAND gate output is 1 after 5th clock pulse because of the Q1 is 0. As and when we are applying the 6th clock pulse, that is negative is triggered, so that when the clock is falling, the NAND gate output is falling to 0. As and when we are applying the 6th clock pulse, Q1 is changing 0 to 1. Whenever the Q1 is changing 0 to 1, both the inputs to the NAND gate are 1, hence the NAND gate output is coming to 0. Once the NAND gate output is coming to be 0, we are looking all the flip-flop clear inputs are 0. Whenever the clear inputs are 0, we are not looking the state of 1, 1, 0. For the user view, it is not visible. We are going to look to the state of the circuit as 0, 0, 0. We are looking here, the clear input of all the flip-flops is 0. When the clear is 0, all the flip-flops are going to be clear. So once we are looking, flip-flops are going to be cleared, immediately the NAND gate output is coming to be 1. Immediately the NAND gate output is coming to be 1. Later, if you go further clock pulses, we are going to look, the same switching sequence is going to be repeated. So that this circuit is now working as mod 6 ripple counter or divided by 6 ripple counter. Is a mod 6 ripple counter or divided by 6 ripple counter. So we are looking here, it is the operation what we are looking from this counter. We are able to look to the answer easily with the knowledge of the circuit 1. Okay, anyway, some circuit is given in the question. While analyzing the circuit, we are able to speak it is a mod value. But truly, our interest is supposed to be not for just analysis. Truly, our interest is supposed to be how to build such mod 6 ripple counter or such mod 5 ripple counter or mod 10 ripple counter or mod 11 ripple counter or mod 12 ripple counter, or in general our interest, our focus supposed to be in general how to build mod n ripple counter. It is a thing we need to understand. Based on this question, it is possible to speak how to build such a mod n ripple counter. To build mod n ripple counter, first of all, we need to identify the number of flip-flops required. To build mod n ripple counter, the number of flip-flops required, let us read the small n. This n we are going to decide based on this condition. Generally, we will be going for smallest possible n value. Generally, we are going to look to the smallest possible n value. So, when we are looking to such mod 6 ripple counter or divided by 5 ripple counter, based on this condition, if at all we are talking the number of flip-flops we need 3. Similarly, when we are looking to the mod 10 ripple counter or divided by 11 ripple counter or divided by 12 ripple counter, the number of flip-flops required will be 4. Okay. It's the one what we need to understand. So we need to bother here for building such a mod n ripple counter, how to recognize the inputs to the NAND gate. Based on this example, what we are looking to build a mod n ripple counter. Of course, this mod n ripple counter, we can look for a further understanding purpose. One case is to the power of n is equal to n. Other case is to the power of n greater than n. Whenever the case is to the power of n is equal to n, there is no need of any discussion required. We already covered this. In the case of this to the power of n is equal to n, what we are looking is the clock of the flip-flop I is coming from the flip-flop I minus 1 output, and external clock is coming directly to the flip-flop 0. There is no need of any discussion. Here our particular interest is for this. Whenever the to the power of n is greater than n, in this case our particular interest. So these examples both are falling under this category. So whenever we are having a situation of the mod n ripple counter for this case, based on this example, it is possible to speak. To build mod n ripple counter, we are using an AND gate. The AND gate output is coming as a clear input of all the flip-flops. So until to this, just it is a story, anything else. We are using an AND gate. The AND gate output is coming as the clear input of all these flip-flops. The important thing here is from where we need to tap the inputs to the AND gate. That is the only one point we need to bother to build in general mod n ripple counter for this case. So from where we need to tap the inputs on AND gate, we can understand again while looking to this example. In this mod 6 ripple counter, we are tapping the inputs to the AND gate from flip-flop 2, flip-flop 1 outputs. In fact, we know well, it is the expected state. It is the expected state, the 6th clock pulse. So based on this, to build in general mod n ripple counter, it is possible to speak. To build mod n ripple counter, we need to use an AND gate. The AND gate output is coming as a clear input of all the flip-flops. That is required because what we are looking by using this AND gate, what we want to look is there must be stopping the clock counting. So we are looking by using this AND gate, we are giving a disturbance in the normal switching sequence. So the normal switching sequence disturbance will be at this nth clock pulse. So for that purpose, we are using an AND gate. Okay. So we need to use an AND gate. The AND gate inputs must be from the flip-flop outputs. The flip-flop outputs, how to choose is a question. It is the flip-flop outputs which are having the value as a 1 at expected nth clock pulse. Whatever the flip-flops which are having the value as 1 at expected nth clock pulse, we are talking, it is expected. The reason is it is not visible in the circuit switching sequence. Mod 6 if you see is not visible. That is the reason. What are the flip-flops which are having the value as 1 at expected nth clock pulse, which are the inputs to the AND gate. And the AND gate output is coming to the clear input. So I am repeating the statement. To build mod n ripple counter for this case, second case, refer to the expected state of the circuit with the nth clock pulse. What are the flip-flops which are having the value as 1 at expected nth clock pulse are the inputs to the AND gate, and the AND gate output is coming as the clear input of all the flip-flops. It is statement what we can make. So if we come to this mod 6, so expected state with this mod 6 we are looking as 110. So whatever the flip-flops which are having the value as 1 at expected nth clock pulse, so n is 6, they are the inputs to 9, that is Q2, Q1, and the AND gate output is coming as a clear input of all the flip-flops. Similarly, if you want mod 5, expected state with the 5th clock pulse, it is a circuit what we are having in fact. Expected state at 5th clock pulse 101. What are the flip-flops which are having the value as 1 at expected nth clock pulse are the inputs to the 9. The AND gate output is coming as a clear input of all the flip-flops. Similarly, if you want mod 10 counter, we need to use 4 flip-flops. Expected state with 10th clock pulse, expected state with the 10th clock pulse 1010, so that the NAND gate inputs must be Q3, Q1. The NAND gate output will be coming as a clear input of all the flip-flops. If you want mod 11 counter, the expected state at 11th clock pulse 1011, so that this NAND gate inputs will be this Q3, Q1 and Q0. The NAND gate outputs are coming as a clear input of all the flip-flops. So based on this understanding, it is possible for us to speak in general we can build mod n ripple counter of any size. We can build based on this knowledge mod 20, mod 25, mod 30, mod 60, mod 50 or anything else we can build based on this knowledge. So it is enough to understand to build in general mod n ripple counter. So finally, whenever we are having a question while giving such sort of circuit, what is the mod value of the given counter if at all we are taking as a question? What is the mod value of the given counter if at all is a question? To answer this question, we are not in need of 1 minute, 2 minutes time. Matter of 20, 30 seconds may be enough to answer to this. So while giving such circuit, if at all we are having a question, what is the mod value of the given ripple counter? The work what we need to do is just we are looking the NAND gate input connections from which flip-flop outputs the NAND gate is having the connections. Those flip-flop outputs will be reading as 1. In this case, the NAND gate is having connection from flip-flop 2, flip-flop 1, so that those flip-flop outputs will be reading as 1. And in general, I am talking other flip-flop outputs are 0. We are going to look to the equivalent decimal number. Based on this, we are going to recognize it's a mod 6 ripple counter. So it is enough work to speak the mod value of the given ripple counter whenever the circuit is given like this. Sometimes we will be looking these NAND gates. For example, for this mod 6, we will be having a connection maybe Q0 complement. For this case, we will be having a connection Q1 complement and so on, even other cases. Whenever we are looking to the Q0 complement as the input of this NAND gate, the default means Q0 complement is 1. So it is only for our understanding sake, Q0 complement 1 means Q0 is 0. Similarly, here Q1 complement is 1. For our understanding, it is nothing but Q1 is 0. So like this, it is possible to recognize, it is possible to understand. So in general, this is the work which is involved in this ripple counters.